Most of the rest of the course is about inference. And so in this short screencast, we just want to introduce inference and talk about the big ideas. So here are some of the kinds of questions we answer with inference. Inference is drawing conclusions about a population based on a sample. We have a sample and we want to draw conclusions about a population. So here's a question. From a survey of 1,000 voters, estimate the proportion who are planning to vote for McKinsey for governor. So use a sample of 1,000 to say something about all the voters. Or, based on a sample of 12 women and 10 men, answer the question, do men and women spend the same amount buying books each year? It's surprising that you can even think about that with such a small sample size, but you really can if it's a random sample. Or from a sample of 1,000 adults, estimate the mean weight of all U.S. adults. Or if you're in the business of, if you run a hospital and you want to know if more than 90% of patients are satisfied with their hospital experience, well, you don't survey all patients, but you might survey 800. So these are the kinds of questions that inference deals with. Using a sample, say something about a whole population. So in statistics, we talk about parameters, and a parameter is a number which describes the population as a whole. So some of the most common ones are population mean, population proportion, population standard deviation. And the symbols we use for those when we're talking about the whole population are the Greek letter mu, the letter p, and the Greek letter sigma. A statistic is the corresponding number for a sample. So if you're talking about an average or the mean of just a sample, we use x with a bar on top. If we're talking about a proportion of a sample, not of the whole population, we talk about p with this little symbol on top, which is pronounced p hat. And if we're talking about the standard deviation of a sample, then we use the letter s. And so the whole point of inferential statistics, of inference, is to use statistics, something based on a sample, to draw conclusions about parameters, something describing the whole population. So there are two kinds of inference that we're interested in. One is estimating, and one is testing a hypothesis. So an estimate is just when you're trying to figure out what a number is, what a parameter is, what proportion of people are planning to vote for McKinsey. So we're interested in the population proportion, and we'll use a sample proportion to estimate that. Or what is the average number of times per year Americans go to the movies, go to the movie theater? So average, that's population mean. Or estimate the difference between the mean income of college graduates and those without four-year degrees. So now we have two means, the mean for college graduates and the mean for those who haven't been to college, and we want to estimate the difference between them. The other kind of inference we talk about is testing a hypothesis, where we have some idea and we want to test to see if it's true. So are more than 50% of the people planning to vote for McKinsey? Or do students spend, on average, more than $1,000 on textbooks? Or will patients taking the new drug Damodol recover more quickly from surgery than those taking a placebo? So will their average hospital stay be shorter? And inference is based on the normal distribution. And it's not quite this simple, but this will give you the idea. Suppose you knew what the standard deviation was for the cost of repairing a certain, for a certain car repair, certain kind of car repair. And suppose the standard deviation was $50, and you had one random car repair that cost $430. So the standard deviation is 50, and one particular one was 430. Well, if you remember, in any normal distribution, 95% of the data is within two standard deviations of the mean. So whatever the mean actually is, 95% of the numbers are within $100 of it. So that $430 is probably one of those, so it's probably within $100 of the mean. So this tells us that the mean is probably between $330 and $530. So we'll see this in more detail later, but the idea is most of the time any one number isn't too far from the mean. How far? Well, 2 times the standard deviation. So if one number is $430 and the standard deviation is 50, then this $430 is probably not more than $100 from the mean, and that would tell us that the mean had to be between 330 and 530. So that would be the big idea behind estimating. one number we can use to estimate the mean. For testing hypothesis, again, it's not this simple, but the idea, suppose an insurance company says that they pay claims on average in 15 days with a standard deviation of 5 days. Well, you choose one claim from the database at random, and it took them 35 days to pay it off. So that's 20 days longer than what they say the mean is. And it's not just 20 days, it's 4 standard deviations. Now, if you use norm-s-dist, you'll see that being a z-score of 4 or more, you'll see that 4 standard deviations basically never happens. It's almost impossible. So if the insurance company were telling the truth, it would be not impossible, but almost impossible that a random claim would take 35 days. And that makes you suspect that they're not telling the truth. And again, the details get messy, and we'll see some of those details later. But the big idea is that in normal distributions, most of the data is close to the mean. 95% is within 2 standard deviations. You can use norm-s-dist to check it out. And 99.7% is within 3 standard deviations. So you can use that idea to estimate and test hypotheses.